So here's some good news. You can do definite integrals in Desmos. The bad news is you can't do indefinite integrals in Desmos, at least not exactly the way we would want to in chapter 5.1. So here we are, I've said f of x equals sine of x. We get a nice sine wave. And you can type an integral and it will compute the net area under the curve for you. And let's kind of talk about what that means. A good way to think of it is x starts at A and goes to B, and we sweep out the area under the curve as x is going from A to B. And here I've shown it in a different color when we're adding up negative areas. So when we write a definite integral from A to B, think of it as x equals A to x equals B, with x sweeping through all the values in between. Also, let me show you how to type an integral here. We'll add a new expression. So I just typed the letters I, N, T, and then when I hit T, it's going to switch it to an integral. And I can put any numbers I want for the starting point and stopping point. So I could say, what's the integral from maybe 0, and then I hit the tab button to go up to the upper end and hit pi. And then I can say f. Now I don't actually have to say x here, even though I defined it. This just means whatever you give it, it does this to it. So I could say f of s ds. And sometimes Desmos takes a little, oh, I already have a variable called s. How about f of q dq? No, I already have a q. Let's see, what's a letter I don't have? Probably a z. F of z dz. And it says the overall area from 0 to pi is 2. That's kind of interesting. So remember, the letter you type here doesn't have to match the letter you used there. And in fact, sometimes there's good reasons not to have it match. Sometimes Desmos takes a little while to recognize what you've typed, and it will give you a warning sign here while it's thinking about that. So if it's doing that, give it, I don't know, 30 seconds or so, and sometimes it'll realize what you meant. Let's take a sec to think about, is this answer of 2 really reasonable for the integral from 0 to pi? We'll bring this back here. How can we check that? Well, we do have these squares. I mean, they don't always look like squares. But here's a unit square, right? From 1 to 2, from 1 to 1. And it just about fills up that unit square. And then there's another kind of half of a unit square here, and another half of a unit square here, roughly speaking. So it seems plausible that the integral here might be 2 total units of area. We could be more careful, and I've actually had to do this in some cases, and count these little subgrid squares. It looks like there's 25 of them per unit square. So we could count how many fall underneath the big curve here. And we could say, okay, well, here's a block of 5 by 4, so that's 20 of them, 21, most of 22, about half of another one, and add up like fractions of little squares. And I've actually, like I said, had to do that to check some of my calculations. So you can compute an area or an integral by counting squares underneath the curve. Let's talk about some other fun ways to compute areas. It turns out long ago, when my mom was a math major, I shouldn't say exactly when that was, but it was about the mid-60s. She said she actually had to compute areas by drawing the curve on graph paper, cutting it out, walking over to the chemistry department and using some of their very delicate balances or scales to weigh it, and then knowing how much 1 square unit of the graph paper weighed, you could figure out what the total area under the curve was. So here's a discussion of some people discussing doing that back in the day for them too. Apparently, people have done this in chemistry since they already had the scales there. If they did some kind of graph on a device and wanted to know the area, the device itself would output the graph on paper, and then they'd cut that out and also cut out a chunk of paper and go weigh them. And not only was this handy in like the 1960s, apparently Galileo himself, like 400 years ago, tried to find an area by cutting a curve out of metal and weighing the metal. So that's a lot of fun. I probably won't require you to do that. Other fun ways to compute areas, there's something called a planimeter, where one end of it stays stuck on the paper, and you move the other end of it around a curve on the paper, and there's a dial that keeps track of how much total area you've swept out. And like a general principle in life, if there's a fun mechanical thing, there's a Lego version of it, so you can watch Lego planimeters computing areas. Let's talk about one other interesting way to compute areas, and that is using something called Monte Carlo integration. Monte Carlo is the name of a city in Europe that has a lot of casinos. And this method was developed in the 1940s by some applied mathematicians working to develop the atom bomb. So that's, I suppose, both good and bad. So the idea there is, let's say we want to integrate x squared dx from 0 to 1. So that's this orange curve here. And we want the area under the curve. If I kind of throw darts at the unit square here, and keep track of which darts fall above the curve and which darts fall below the curve, then if I knew that I threw, here it's 100 darts, and if I find that, what does that look like? Maybe 30 of them fell under the curve, then I would say the area under the curve is 1 out of 3, or 30 out of 10, 30 out of 100 of the entire area of the square I'm throwing the darts at. So here I've got a random number between 0 and 1, so that's a random x coordinate. I've got a random number between 0 and 1, that's a random y coordinate. There we go. Here I'm computing the value of f of x, and then just saying, is my, my y value here less than the associated value of f of x? If it is, give me a 1, otherwise give me a 0. And then we're saying take the average of these so far. If you take the average of things that are zeros and ones, that's basically taking the proportion of them that are ones, or it's counting all the ones and then dividing by the total number of things you've tried. So this is only 100 dots that I'm showing, but in the spreadsheet I've got it actually set up for 10,000 trials. And let's see how that running average behaves as we do more and more trials up to 10,000. Looks like it's pretty much stabilized around, what is that, maybe 0.3-ish? And I can get new random numbers and see how you can see the curve varies a fair bit early on, but by the time you get down here, it doesn't vary very much. And you might say, well, how do I know how many trials is enough? Well, it turns out that's what we use statistics for, right? You might have heard of confidence intervals. We can do confidence intervals on this kind of thing and say, how many trials do I need to get within a certain tolerance? And this might seem horribly antiquated, right? If it was invented in the 1940s to do atomic physics research, but it's actually useful today in doing Bayesian statistics. Bayesian statistics. And there, they're not doing it just in one dimension, they're doing it in multiple dimensions, 10 or 100 or 1,000. So it's an interesting technique. If we do this in class, we often like draw a big square on the chalkboard and have people kind of close their eyes and throw chalk at the chalkboard so it leaves a little mark. But it's hard to do that in online classes. So that's some interesting ways of doing integrals, both modern, using Desmos, and so here's another computation like f 0 to 1, 1 to 2 f of x dx, and it just computes it. How does it compute it? It's not using antiderivatives as far as I know, and we'll talk more about how Desmos might be computing that in chapter 5.3 and 5.4 and 5.5. So going from the modern methods all the way back to the older methods and the older methods still.